Good morning, students. We will continue with the D and F block part, and today we will conclude this chapter. We'll be finishing the second half, that will be the actinide series. Now, before we go with the actinides, a recap what we did last time. We spoke about lanthanides, that's the first inner transition series. They were also called rare earths, alright, because earlier the ores were rare in the earth's crust. Now, in this first inner transition series, we will say they are collectively called as lanthanides or lanthanoids because this name is a prototype. It's basically the name lanthanum. After lanthanum, a series of 14 elements having similar properties. That's why the word prototypes. Now, with respect to lanthanides, I gave you a mnemonic to memorize, okay? Because for 14 elements, that is 58, that is cerium to 71. Is this clear? That's lutetium. What was it? We include lanthanum. Oh, please understand once again, lanthanum is not a F block element. It's a D block element. It's only considered with respect to its property. So the mnemonic, what was there? The catchy mnemonic what I gave you, lanthanide chemistry provides no problems since everyone goes to Despo Harshad's extra thorough yearly lectures. Alright, so that was the mnemonic what we had. Today we will be continuing with the general characteristics because last time we spoke about the electronic configuration and its oxidation state. What was the concept with respect to the oxidation states? All lanthanides or all inner transition elements have a common oxidation state of +3 where they also show +2 and +4. +2, that's the lower oxidation state where they are good reducing agents, and +4 where they are good oxidizing agents. So reducing agent +2 increases to +3 and good oxidizing agents +4 reverts back to +3. Alright, we will start with the part now, people. Alright, let's start here. So first part, people, what we have over here, that is we'll be talking about the general characteristics. I'm just gonna read out over here. I want everybody just concentrate over here, please. Now mainly it says all lanthanoids are silvery and soft metals and they tarnish rapidly in air. What does this mean? They readily undergo oxidation to form their oxides, which are more stable in their +3 oxidation state. So any metal, so these are mainly all electropositive metals, because metals, when you cut open a surface, is this clear? Then the metal surface gets tarnished because there is what we call as our photoelectric effect is happening. So that's the tendency is more to get readily converted to its oxidation state of +3. That's one. Then the hardness increases. Yeah, the melting point ranges between, but samarium is the one which melts at a different temperature, 1623 Kelvin. Then it says typical metallic luster. Yeah, density changes smoothly except for europium and ytterbium, and occasionally for samarium and TM, that is thulium over there. Then they are generally, these are the many trivalent means +3 state. They are all colored both in their solid state and as well as in their aqueous solution, and the color is because of the presence of F electrons. Now if you all remember, we discussed this in D block again over here. F block elements also show color. The answer is simple, crystal field splitting theory. When light falls, is this clear? Then if there is presence of unpaired electrons, then that unpaired electron will jump from a F orbital of lower energy to F orbital of high energy. We all know the F subshell is made up of 7 orbitals. So the 7 orbitals will split into lower and higher. So unpaired electron jumping from lower F orbital to a higher F orbital. That's called FF transition. In D block it was DD transition. Here it is FF transition. So anytime a question comes or an MCQ comes with respect to color, color is always because of the presence of unpaired electrons. In D block it's DD transition, F block it is FF transition. That's one. Then it says however absorption bands, yeah, the lanthanoid ions are all except now generally all are paramagnetic, matlab weakly attracted except the ones which are empty or completely filled. That is, look here please, F0 configuration, that's lanthanum and cerium 4+, because cerium is 58, so it loses all the 4 electron, it becomes 54. That's the configuration of xenon. And F14 over here, that's Yb2+ and Lu3+, ytterbium and lutetium. So except these, that's empty or completely filled. if we say all are paramagnetic, so they are weakly attracted. Then the first I values it says are around 600 kilojoules. The second goes to somewhere around 1200, comparable to those of calcium it says. And the third I value indicates that the exchange enthalpies, as in case of 3D orbitals of the transition series, appears to impact a degree of stability of empty, half-filled and completely filled orbitals. So in the third I people, it is talking about the stability rule. That is, the empty, half-filled and the completely filled orbitals are more stable than the incomplete orbitals. That's one. Moving next. Now next part people, what are you going to talk, what it says, the abnormally low value of the third ion enthalpy, that's of lanthanum, gadolinium and lutetium. This is where it was D0 for lanthanum, gadolinium was D7 and lutetium was, sorry, not DF. For lanthanum it was F0, gadolinium was F7 and lutetium was F14. So empty, half-filled and completely filled. Then next is people the E0 values. We all know what is the E0, standard electrode potential value, which is with respect to, I've told you, it's how you get the E0 values, combination of three things. One, it's first of all it's sublimation from solid to the gas. Second, ionization, that is to form its ions. And third, it's hydration enthalpy. So combination of three, that is sublimation plus ionization plus hydration, gives us the E0 value. If the E0 value is more for reduction, it is placed above hydrogen, less for reduction but more for oxidation, then that is with a negative value of SRP placed below hydrogen. Clear? That's the part. Now all people Ln3 plus, Ln is basically a general way to write all lanthanides. Remember, Ln is not lanthanum, lanthanum is La. Ln is a general form for all lanthanides, 58 to 71. So they all 3 plus will gain electrons and form Ln, matlab they undergo reduction, and all values if you observe are all negative. Negative means I just now told you they are all placed below hydrogen. So all this inner transition elements all are strongly electropositive metals. Where it says europium has a value of -2, that's an exception there. That's because of the half filled. That's F7. Then people, we have some of the properties as they are metals. They form the carbides, the different compounds. Like if you remember, we did know alkynes, calcium carbide with water gives acetylene, same way. So Ln3C, where Ln is all lanthanides. So these are the different types of lanthanum carbides it forms when heated. Then it says it liberates hydrogen when it reacts with dilute acids. That's a confirmation. Any substance which is a metal when reacts with an acid liberates hydrogen gas, and they burn with halogens to form their halides, that is again in +3 state. And they also form their oxides. There also, if you see, it's +3 as well as its hydroxides. All right, the hydroxides, yeah, they are definite compounds. They are basic like alkaline and like alkaline earth metal oxides and hydroxides. So across a period, people, from left to right, the basic character decreases. So if I start with lanthanum, which is actually a D block, but for the consideration part, we have lanthanum hydroxide over there, that is the strongest base, and then gradually it will decrease, and lutetium hydroxide would be the weakest base because they are metals. So metals, we have discussed, they have more tendency to readily undergo oxidation. As they undergo oxidation, they are good reducing agents, and reducing agent always forms a strong basic oxide. Clear? So if I just say only the lanthanide series 58 to 71, cerium hydroxide would be the strongest base and lutetium hydroxide would be the weakest base. That's one. Then people, one important use is in the production of alloys over here, where a very known alloy, people, this name you have to know it from a factual point if they can say MCQ, mesh metal, which has around lanthanoid metals are around 95%, iron is 5% with traces of sulfur, carbon, calcium and aluminium. And this mesh metal is clear, is mainly it's used in magnesium based alloy to prepare bullets, shells and lighter flints. So basically the cartilages, whatever are the small amount of sharpeners which are present, is clear, or we can say the bullet shells and all, they are made up of mesh metal. All right. Also it says it's used as a catalyst in petroleum cracking. We know cracking, right? Breaking a higher hydrocarbon into lower ones, that's cracking. And it says some lanthanides are also used as phosphors in television. Phosphors is basically what, people? material when exposed, it is clear, to radiation, it emits visible light. That's what we call as a phosphor. So any fluorescent color is basically a phosphor, and it says in similar fluorescing surfaces. That's one. Then next we have people, this is just a table. So with acids, is this clear? Please see this carefully. With acids, it liberates hydrogen gas. With oxygen, just see the slide please. With oxygen, it forms its oxide, that's lanthanum oxides, all in +3. With halogens, it forms LnX3, that's again in +3. With water, it forms its hydroxide. So that confirms they're all strongly basic. With carbon, at different temperatures, so at such a high temperature of 2773 Kelvin, it forms lanthanum carbide. With nitrogen, lithium is lanthanum, lanthanum nitride. Nitride is N⁻�3-, and with sulfur, it's lanthanum sulfide. Okay, so these are some of the, we don't have any reactions as such, but just to know what it forms. Okay, that's one. Now a very important part, people, actinoids. See, from F block, know the configurations very well, as well as the lanthanoid contraction, what we discussed last time. That is a small decrease in size across the lanthanide series because of the poor shielding of the F electrons. That's why, remember, I said post lanthanides we have 4 pairs of chemical twins: zirconium hafnium, niobium tantalum, molybdenum tungsten, technetium rhenium. The 4 pairs of chemical twins, where down the group their sizes are similar. Now configuration, people, look at that. So we have now we are discussing again actinium in the actinide series, because actinium is a prototype. Actually actinium is where 3rd group 7th period in the D block, but only because of similar properties we are considering. So if I say is actinium an actinoid, no, it's a D block element, because for actinium, just see here again 2 configurations. So we are discussing actinium for that. It's basically 90 to 103. I'll give the mnemonic for this also. It's very easy, you'll remember it. In fact, this is the easiest of all. Now look at this. As per the OFBA, all should go into 7s2. So just look at this expected, what I'm highlighting on the slide, please. In expected, all are 7s2 throughout. All is 6d1, because that's the anomalous behavior. Technically, if you see the energy gap between, as per the OFBA, after 7h it should have gone into 5f and then into 6d, but because of the less energy difference between 5f and 6d, one electron only goes into 6d, and that one remains throughout, and then the 5f starts filling up properly. So look at that, actinium is 5f0, matlab electron is not in the F block. That's why actinium is a D block. It starts from thorium onwards, F1 to F14. This is the expected as per OFBA, but the observed is not the same. Again, we have certain anomalous behaviors here. Observe this very well, something very important. Now first case actinium, we have this as F0. So as I told you, it's not an F block, it's a D block. Thorium, people, atomic number 90. Just look at this observed. People, F1 should have gone, but what is happening? Because of the less energy difference between 5f and 6d, straight away 2 electrons jumps into 6d. So we have a very anomalous configuration, 62. Technically all should remain 61, but the X-ray, the spectra, what we have, the spectra shows that there are 2 electrons in its 6d orbital. There, F is still empty. And when we start with protactinium, is this clear? That is Pa. It starts back, 61 comes, and 1 electron from the 60 goes back to 5f, and the new electron what enters also goes into 5f. So straight away it becomes 5f2, and then this 6d1, if you observe, people, it is retained till Neptunium. So till Neptunium, people, it retains the 60 electron. So this, if you observe, people, what I'm trying to talk is this, the 61 electron. Alright, if you observe, this 6d1 is retained. Is this clear? That's the part. In fact, one exception, that is of thorium, where it becomes 62. And again, people, if you observe, then this becomes, again, people, the next one, when it starts plutonium over there, it becomes 6d0, and that shifts back over there. So basically, what is the understanding? Normally 1 electron stays, that what we see in lanthanum, only when it was empty, half filled and completely filled. That was for lanthanum, gadolinium, and the last one, lutetium. Okay, here in this case, people, the 1 electron is there, but in case of thorium, an exception, straight away 62. and then till Neptunium people the 61 is electron is retained, and then it reverts back to 5f. And then again people, if you observe americium 95, where it acquires, just see here please in the observed 5f7 it becomes. So after 5f7 the next electron what comes, that's for curium, behind the name Madame Curie. Then it becomes straight away 5f7 ke baad one more electron goes into 60. So with respect to half filled now, so again one goes, and then from berkelium people, Berkeley, the place where the chemist Seaborg had its laboratories, where he discovered these elements. So here if you observe people, again it becomes D0 and the new electron goes into straight away as 5f9 over there, and then it continues till it comes to nobelium, that's 102, that is f14, and then the last element people lawrencium 103 there, what we have. Straight away people, again that new D1 electron comes. So the gist, as I told you, whenever they ask configuration, never write expected except if they ask you specifically what is the expected, otherwise it's always observed. Here people, we say the 6d electron mainly retained by 3 to hai, that is empty, that was for actinium. Half filled what we see, that's for curium, and completely filled, that's for lawrencium. But in between we have thorium which has D2 exception until 93, that is basically from when I'm starting from 89 to 93 the 61 electron is retained. Clear? Now the mnemonic for this, very easy, listen carefully. Active thorium, please see the slide. Active thorium protects Uranus, Neptune and Pluto, because the names are with respect to the planets. Next sentence. American curry was prepared in Berkeley and California, while Einstein, Fermi and Mendeleev made noble laws. I repeat the whole part. See, because here no, you have the planets, you have the name of the places, name of the scientist. So you put up everything together. I repeat the whole thing. Please pen this down somewhere. This will help you. From this chapter, see, it's only 21 to 30 to know. Rest I told you, it's only the first and last of the entire transition. Like for example, 3D, all scandium to zinc, science teachers, what I gave you. Then 4D series, that's yttrium 39 to cadmium 48. 5D series, La57. Then immediately next was hafnium 72 to mercury 80. Last actinium 60 series, actinium 89. Then straight away 104, that's rutherfordium, till copernicium Cn, that's 112. Okay, that is the way how the whole part works over there. In this category people, we have to know this lanthanides and actinides. So the D block, full lanthanide series and actinides. Once again the mnemonic. Active thorium protects Uranus, Neptune and Pluto. Next sentence. American curry was prepared in Berkeley and California, while Einstein, Fermi and Mendeleev made noble laws. Okay, so that's how the mnemonic part goes. So always when you have a paper or something, say the mnemonic and write the symbols and put the atomic numbers. It becomes easy to work. Okay, now compared to lanthanoids, so if you remember, I told you in the entire series of D block there was only one man-made element, that was technetium. In F block people, the story is little different. We have actinoids are generally over there, what we have as these are the radioactive elements over there, because we know now post 82 all after lead, all are basically the radioactive substances. It says where the half-lives people, half-life of a radioactive substance is its characteristic property, where we say shorter the half-life, more harmful is the element, because it will give out disintegrations in the form of alpha, beta particles and gamma rays. So look here, like for example the half-lives, it says it ranges from a day to 3 minutes. Like lawrencium, the half-life is only 3 minutes, meaning if I have 1 gram of lawrencium to disintegrate to 0.5 grams, that is half the time taken to disintegrate will be only 3 minutes. So it'll give out more disintegrations, so it's more harmful. Then the next part, now we have the electronic configuration, what I discussed quickly over there. So people, nearest inert gases, radon, what we have, that's atomic number 86. Just have a look at the slide please. So the short part, we don't write this whole configuration of 1s2, 2s2 till 6p6, that's radon. So 89 radon straight away is written as radon 61 7s2. Now the part, the exceptional configurations, why they are, this line important. The energy difference between 5f and 60 is very small, and therefore the lighter members, that is thorium to neptunium, they retain the 6d electron. Alright, So it says the 5F level becomes progressively lower in energy as compared to 60 levels. So thorium is an exception where straight away it is 62 and 5F is 0. Americium is half filled, 5F7. So there is extra stability after americium that we see in curium, where one electron goes back to 60. So the general configuration of actinides, you have to read it backwards: 7s2, 60 0 to 1, 5f1 to 14, where technically it should have been 60 0 to 2, but thorium is an exception. So generally if the configuration comes, always we write 60 as 0 to 1. So last three shells incompletely filled: 7, 6 and 5. Alright, that's the configuration. Next, the ionic size. People, ionic size, they all are stable in +3 oxidation states. And here, what do we say? We spoke about lanthanoid contraction. Here, the actinoid contraction will be much more as compared to the lanthanides, because compared to 4F, 5F are the one which will be shielded more over there because they are deep inside. So if the shielding is there, then again over there, no doubt again 5F shielding will be poorer. So the contraction will be more. So compared to lanthanide, actinide contraction is greater. So that's what it says. There's a gradual decrease, or it's M3 plus size. It is referred to as actinoid contraction. Once again, what will be the actinoid contraction? As the electrons are going into the pre or the anti-penultimate shells. Is clear? Because outermost is valence shell, then penultimate, and then last but two is pre-penultimate or anti-penultimate. So there the electrons are in the F subshell, which shows still weaker shielding. So the valence shell gets contracted. So like lanthanoid, we also have actinide contraction, and it is greater for the element of this series. Why greater? Because the shielding as compared to lanthanides, actinides is in the 5F, so the shielding is still poorer. Okay, so the valence shell will be contracted more. Now comes people like how we spoke in lanthanides. We have the oxidation states with respect to actinides, where if you see people, just look at this table, except thorium, people all are having +3 state. So +3 is the maximum stable oxidation state. And if you observe, as we go, the oxidation states are going on increasing. Like thorium has 4, proactinium goes till 5, uranium 6, neptunium and plutonium has 7, and then it goes on decreasing like that. Okay, so once again maximum goes till +7 because you're using electrons from 3 shells. And now see in lanthanides, if you observe, then with respect to lanthanides, you had the valence shell as 6, 5 and 4. It was that way. Here it is 7, 6 and 5. So you are still inside. So the electrons are being exchanged. Now what it says here, see here. Yes, it is because of the comparable energies of 5F, 60 and 7S. That is outermost, penultimate and pre-penultimate. Then +3 is the common oxidation state what we have. Now here it says in the first half of the series, they frequently exhibit higher states, that is 4, 5, maximum neptunium and plutonium, that is +7 oxidation state. And then they says they have more stable compounds in their, like the lanthanoids in +3 rather than in +4 state. And +3 and +4, the ions tend to hydrolyze. Matlab, the stability is more in +3. And here also the same way. Lower oxidation state, they will be good reducing agents. Higher oxidation states, they will be good oxidizing agents. Clear? That's one. Now people, you want to talk about general characteristics. All right, this is the last part because we don't have any chemical properties with respect to actinoids. It's just the configurations over there. General properties. We have distinction between lanthanides, actinides, and the similarities. That's it. The topic is done. Just see here now. They're silvery metals. I'm just reading the slide. Please observe the slides well. They're highly reactive. The actinoids, it says, are highly reactive when they are especially in the finely divided part, because metals na surface area will be more. Then forms its oxides on reaction metals. Hydrochloric acid reacts all the metals, but most are slightly affected only by nitric acid, because we all know nitric acid forms a protective layer of oxide on its surface. That explains the passive part. Then magnetic properties, people for D block part, we said the lanthanides over there, except when it is what I can call as empty or completely filled. They show paramagnetic behavior. So here also we have people, the actinoids, they will form more complexes, like we spoke about complex formation in D block. Lanthanides also form complex because of vacant orbitals available, but actinides, the complexity will be more because you have over here you have nothing but the 5D orbitals. That's why. Then people, it says the magnetic susceptibility with the number of unpaired 5f electrons is roughly parallel to those in the terms of lanthanoids. Alright, that is one. Now in this case, people, what is the part over there? What we have is, next part it says over there, the latter have higher values. It is evident from the behavior of the actinoids that the IE is nearly the IE of early actinoids, although not accurately known, but are lower than the lanthanoids. This is reasonable since it is to be expected that the 5f orbitals are beginning to be occupied. They will penetrate less into the inner core. Why will they penetrate less? Because the shielding is poorer as compared to 4f. That's why. And people, here we have a formula. If you remember, for D block we had a formula that's a root of n into, over there nothing but n plus 2. Here there's a different formula for F block, nu, that's the magnetic moment, that's root of 4s into s plus 1 plus L into L plus 1. S corresponds to, over there nothing but the, as we all know, S corresponds to what over there, people? S will be the, with respect to the spin over there, and L, when I'm talking, L basically corresponds to your azimuthal quantum number. That's one. Okay, moving next, people, what we have now we have a comparison, people, over here between lanthanides and actinides. Just have a look at the slides. It says all are stable, all lanthanides are stable except promethium. So promethium is the only radioactive lanthanoid we have. So for T block it was technetium, which was the radioactive lanthanoid. With respect to that was for D block. For lanthanide series, all are naturally occurring except promethium, that's a radioactive one, whereas actinoids all are radioactive. Now here, people, apart from plus 3 they show plus 2 and plus 4. Here, people, apart from plus 3 we can have higher, like plus 4, and it can go up till plus 7. Then all are, people, they are tri-positive, matlab plus 3 state, they are faintly colored, whereas here these compounds are deeply colored. People, the logic of being deeply colored, 5f ka shielding is poorer. Lanthanides have less tendency for complex formation, actinides have more tendency. Again, the reason, because of the poor shielding part, the 5f electrons are readily available. So more orbitals available vacant, more tendency for complexes. Because for complex we require three things. One, small size, greater polarizing power, charge by radius ratio, and third, availability of vacant orbitals. Then lanthanides, they will be less basic, whereas here we say actinides are gonna be more basic character, because they are the ones which will be more basic. Again, the reason same, poor shielding. Alright, so here we say, here the magnetic properties are explained, that's its paramagnetic part, whereas here they cannot be explained because electrons are from, again, the 3, but they are deep inside. Then greater shielding is there of 4f. So if the shielding of 4f is more, the contraction in radii is lesser. This is an important point, the 7th one. Whereas for actinides, there's a poor shielding of the 5f because it's deep inside, so contraction is more over there. Understand, people? If the shielding is weaker, the valence shell will be pulled more towards the nuclei. So compared to lanthanides, actinides, the 5f ka shielding is poorer, so contraction is more, so actinide contraction is greater as compared to lanthanide contraction. Lanthanoids cannot form oxocations. I've told you what is oxocations. We discussed this in D block. Oxocations, cations with oxygen over there in their respective oxidation states. So like look at UO2 2+, uranyl dipositive cation, or PuO2 2+, that's with plutonium and just UO. So with oxygen, these elements forming their oxidation states. The binding energies are higher. What is binding energy, people? Binding energy, the energy by which the protons and neutrons are held inside the nucleus. So for 4f the binding energy is more, for 5f it is weaker because of the poor shielding. Then comes, people, here, name a member of the lanthanoid which is a well known in +4 state, people. That definitely is cerium there. Why? Cerium basically has 4 electrons. That's the first lanthanoid we have. So if it loses all 4 electrons, alright, then what's going to happen, people? For the cerium, it acquires the configuration of state away xenon. So that's why in the +4 state it is a good oxidizing agent. Next, people, actinide contraction is greater from element to element than the lanthanoid contraction. Again, the same reason. In case of lanthanides, the pre-penultimate shell is the 4f subshell. For actinoids, the pre-penultimate, that is the last but 2 shell, is the 5f subshell. Compared to 4f, 5f ka shielding is poorer. shielding is S greater than P greater than D greater than F. So if F ka shielding is poorer over there, the valence shell is contracted more. So hence we say the actinide contraction is more as compared to lanthanoid contraction. That's the part. People, last part we have now, we have to talk about the similarities that is between lanthanides and actinides. They all are good reducing agents, more stability in +3, so they are good conductors of heat and electricity. Then all the ions, they will show paramagnetic properties except when they are either empty or they are completely filled, like La3+, Ce4+, they have F0. Ytterbium 2+, lutetium 2+, they have F14, so they are completely filled, so they will not show paramagnetism. That's an important point from MCQ. This point, please highlight this. See on the slide, please. Paramagnetism is maximum in neodymium because neodymium shows maximum oxidation state. So I've written there magnets. Magnets, what we use, those are the neodymium magnets what are there. So that has maximum paramagnetism. Okay, that's one. So promethium, the only what we can call as the synthetic or what we can call as the radioactive lanthanoid. Here magnetism wise, paramagnetism maximum with neodymium. Both the series have colored ions, but compared to lanthanide, actinide compounds are deeply colored. Both show contraction, that is lanthanide as well as actinide contraction is observed, but actinide contraction is greater than lanthanoid contraction. They have high melting and boiling points. Then people, they are nitrates, that's NO3 minus, perchlorates, ClO4 minus, and sulfate, SO4 2 minus of actinides and lanthanides are soluble, whereas they are hydroxides, fluorides and carbonates, OH minus, F minus, CO3 2 minus, they are insoluble. Then color part, in the absorption spectra, it says both show sharp line-like bands due to FF transition. So compared to lanthanide, actinide compounds are deeply colored. Alright, so that's because of the FF transition. I told you FF, lower orbital of F to a higher orbital of F. Then both lanthanides, actinides, they form complexes, but complex formation is more with actinides like EDTA. This compound is ethylene diamine tetraacetic acid. It forms its ions called ethylene diamine tetraacetate ions, which is a hexadentate ligand. Hexa, 6 points of attachment. I'll just tell you the structure, listen to me carefully. Ethylene, so CH2CH2, just write down the structure. CH2-CH2. Now on CH2, you have diamine and then you have tetraacetic acid. So on CH2 down, you will put NH2NH2. And on CH2 up, each part you will put COO minus. So listen carefully. CH2, single bond CH2. On one CH2 up, COO minus. Down below CH2, NH2. Then same way on this part, the mirror image. CH2, CH2, so the right side CH2, up CO minus and down NH2 minus. How 6 points of attachment? On nitrogen, each nitrogen 1 lone pair, so 2 points of attachment. Every oxygen COO minus has got over there 2 lone pairs. So each oxygen has 2. This oxygen on the right also has 2. So 2, 2, 4 plus 2. So total 6 points of attachment. So there are 6 places by which it can donate its lone pair. That's why the word hexadentate ligand. We'll be talking about this when we do coordination compounds. All right. Ligands we know now. They are the compounds. They are either cations or anions or neutral species capable of donating lone pair of electrons in the vacant orbitals of the metal. Then they are lustrous people, matlab they get tarnished in air, matlab they readily form their oxidation state, that's +3, and or both form their hydroxides, that's the OH ions, which are ionic and basic, where actinides are more basic as compared to lanthanides. Then next we have people some basic applications. These are the uses part. What is there? Like TiO, titanium oxide, that's for pigment industry. MnO2 is used in dry battery cells. That's like a depolarizer. We'll be talking about this in electrochemistry when we come to dry cell. Then it says the elements use zinc, nickel and cadmium, the batteries. So it says the elements of group 11. Group 11 people, transition series, is this clear? These are mainly called the coinage metals. What are the elements of these group 11? Copper, silver and gold. Earlier coins were used now, made up of copper, silver and gold. That's the part. Then V2O5 people, vanadium pentoxide. that's for the catalytic, that's use of the catalyst. People Haber's process, not Haber's. Haber's was ammonia. Contact process, preparation of H2SO4, where we have oxidation of SO2 to SO3 in presence of V2O5, vanadium pentoxide. So V2O5, first SO2 in the presence of V2O5 gets oxidized to SO3, and in the presence of atmospheric oxygen, V2O4 is again oxidized back to V2O5. So catalyst took part, formed an intermediate, reaction got over, the catalyst was regenerated. So that's one. Then people, this is an important one. TiCl4, that's titanium tetrachloride with trimethyl aluminium. CH3 is methyl 3 times, so trimethyl Al. That is the basis of a catalyst, Ziegler catalyst, that's used for the manufacture of polythene, that's plastics, that will be doing in polymers. A Ziegler-Natta catalyst, which is a combination of titanium, TiCl4, titanium tetrachloride along with trimethyl aluminium. Then iron, people, that's a catalyst for Haber's process, that's nitrogen and hydrogen giving ammonia with iron as a catalyst and molybdenum as a promoter. Then nickel catalyst, people, we know that's used for the hydrogenation of fats to oils. People, if you remember, is this clear what we have? So if you remember, hydrogenation reaction, people, different, you have generally people converting normal hydrogenation, we have oils to fats. So here hydrogenation can be done, is this clear? So this part has to be hydrogenation of oils to fats, where if anybody remembers, hardening of oils in the liquid state are converted to fats in the solid state. So this line should be hydrogenation of oils to fats. Okay, it should be, this is a misprint over here, so please clear that part. Okay, that's one. Then people, we have a process that's called Walker process, that's oxidation of alkynes, that's ethyne to ethanol. Ethanol is, people, acetaldehyde. So that's catalyzed by PdCl2, that's palladium chloride. So palladium chloride is a catalyst for Walker process, where you straight away oxidize ethyne to acetaldehyde. And next, people, we have nickel complexes, that's for the polymerization part, where it forms nickel acetylide, or what we have compounds called as organo-nickel compounds, matlab carbon atoms bonded to nickel, where nickel provides its vacant orbitals and we have the complexes formed. And last, people, point, the photographic industry, a special property of a compound that's of AgBr is used over there, that is silver bromide. That's it, people. We are done with this chapter. This chapter is over here. All right. Okay. Thank you.